So what really makes an acid strong versus weak? It seems like a simple question, but in chemistry, that word strength has a super specific meaning that gets mixed up all the time. In this explainer, we're going to break down that crucial difference and get to the bottom of it.
When you hear the words strong acid, you're probably picturing something that can just sizzle right through a piece of metal. And yeah, sure, some can, but that's not actually what chemists are talking about when they say strength. The real scientific definition is way more precise, and it all comes down to one single key process.
Okay, first things first, let's get the biggest misconception out of the way. Strength is not the same thing as concentration. Think about it like this. Strength is like the raw power of a single punch. It's built in. Concentration is just how many punches you're throwing. So you could have a whole bunch of weak punches, that's a concentrated weak acid, or you could have just a few really powerful ones, a dilute, strong acid. They're two completely different ideas.
All right, so if strength isn't about concentration, then what is the true measure? Well, it all boils down to one simple process: ionization.
This right here, this is the moment of truth for any acid. When that acid molecule hits the water, does it give up its proton, that little H, to a water molecule? For a strong acid, the answer is a resounding yes. It's pretty much a one-way street. But for a weak acid, it's a lot more hesitant. That reaction just barely gets going.
Picture a party. You've got 100 acid molecules in a beaker of water. If it's a strong acid, like hydrochloric acid, every single one of them is going to break apart and give away its proton. It's a total giveaway. But if it's a weak acid, like the acetic acid you find in vinegar, maybe only one or two decide to join the party and ionize. The other 98 or 99, they just hang back totally intact. So strength is really just a measure of this willingness to break apart.
But saying a little or a lot isn't really precise enough for science. To actually compare acids, chemists needed a scorecard, a real way to put a number on strength.
And that number is the acid ionization constant, or just Ka for short. You can think of it as a ratio. It's the amount of broken apart ions on top divided by the amount of intact acid on the bottom. So if an acid ionizes like crazy, you get a big ratio and a large Ka. If it barely does anything, the Ka is going to be tiny. It's literally the official power ranking for acid strength.
So let's actually put this to the test. Let's compare these three weak acids. Acetic acid has a Ka of 1.8 times 10 to the negative 5. That's a pretty small number. Nitrous acid's Ka is a bit bigger, 10 to the negative 4. And then you've got hydrogen sulfate, which is stronger still, at 10 to the negative 2. It's really simple. The larger the Ka value, and remember, a smaller negative exponent means a bigger number, the stronger the acid. It's a direct reflection of how much of it broke apart.
And hey, this isn't just an acid thing. Bases have their very own scorecard, the Kb, or the base ionization constant, and it works the exact same way. It's a measure of how well a base makes hydroxide ions in water. A bigger Kb just means a stronger base. Simple as that.
Now this is where it gets really interesting. See, acids don't operate in a vacuum. Every single time an acid gives up its proton, it creates a partner, its conjugate base. And the fascinating thing is how their strengths are connected in this perfect balancing act, kind of like a seesaw.
This right here is one of the most important rules in all of acid-base chemistry. I'm going to say it again. The stronger the acid, the weaker its conjugate base. And, of course, the opposite is true too. The weaker the acid, the stronger its conjugate base. It's a perfect chemical seesaw. One goes up, the other has to go down.
And there's this beautifully simple piece of math behind the magic. The Ka of any acid multiplied by the Kb of its conjugate base always equals this tiny little constant called Kw. That's the ion product for water. And since Kw never changes, if the Ka value goes up, the Kb value has to go down to keep the whole thing balanced. It's a mathematical certainty.
Okay, let's watch this seesaw in action. Take a super strong acid like HCl. Its Ka is so huge, we basically just say it's infinite. Well, that forces the Kb of its partner, the chloride ion, to be basically zero. Chloride is a terrible base. Now let's flip it. Look at a weak acid like ammonium, an H4+. Its Ka is tiny, I mean really tiny. And because of the seesaw, that means its conjugate partner, ammonia, NH3, has to be a pretty decent weak base with a much larger Kb. See? The seesaw is always in perfect balance.
Okay, so we know what strength is, and we know how to measure it. But that brings us to the biggest question of all, right? Why? Why are some acids stronger than others? Well, the answer isn't just random. It's actually hidden right inside the molecule structure. It's all about the bonds. For the really simple acids, the ones with just 2 atoms, there are 2 trends on the periodic table that tell you everything you need to know. First, as you go down a column, the bond holding that hydrogen on gets longer and weaker, more fragile. It's just easier to snap. That's why HI is a much stronger acid than HF. And second, as you move across a row, the other atom gets, well, greedier for electrons, more electronegative. It starts pulling all the electron density away from the hydrogen, which weakens its connection and makes it way easier for that proton to just pop off.
Now, for the more complex acids, the oxyacids, things get even more fun. It basically turns into a multi-way tug-of-war for electrons, and the whole battle is centered around that one critical bond between an oxygen and a hydrogen.
2 simple rules decide who wins this tug-of-war. First, if you have a greedier central atom, one that's more electronegative, like sulfur compared to selenium, it pulls harder on all the electrons, which weakens that OH bond and makes for a stronger acid. And second, adding more oxygen atoms to that central atom is like calling in reinforcements for your side of the rope. They all pull electron density away, making that OH bond incredibly weak and that little proton ready to pop right off. That's exactly why sulfuric acid, H2SO4, is so much stronger than sulfurous acid, H2SO3.
So, what's the big takeaway here? It's that acid strength isn't some random property. It is a direct result of the molecule's architecture. It all comes down to one question. How easy is it to break that hydrogen off? And the answer is written right there in the bonds, the atoms, and their constant tug-of-war for electrons. It's all connected.
But this brings up a really fascinating puzzle. See, in water, all the strong acids, HCl, HBr, all of them, they seem to be equally strong. Why? Because they all ionize 100%. Water is just such a good base that it rips the proton off of any strong acid no problem. This is called the leveling effect. Water basically levels the playing field, and it makes it impossible for us to see the subtle differences in strength that might exist between them. And that leaves us with one final really cool thought. If you actually want to rank the strong acids against each other and find out which one is the true champion, you can't do it in water. You have to change the game. You've got to take them out of water and put them in a different solvent, one that's a much, much weaker base. Only then, when the conditions are tougher, do they start to reveal their true, distinct strengths. It's just a perfect reminder that in chemistry, context is absolutely everything. Thanks for joining this explainer.